Before applying a voltage to the p-n junction, we have to define the polarity first. For a p-n junction, the symbol is shown here. The left terminal here represents the p side of the p-n junctions, and it's also called the anode. The right terminal here represents the n side of the junction, and is also called the cathode. When a positive voltage VA is applied to the p side with respect to the n side, it is called positive bias or forward bias. When a negative VA is applied to the p side with respect to the n side, it is called negative bias or reverse bias. We will first look at the condition of reverse bias before going to the forward bias. At reverse bias, a negative VA is applied to the p side of the junction and raises the water level. It breaks the alignment of the Fermi levels on the two sides of the junction, and the junction is no longer at thermal equilibrium. As Fermi level is just like the water table, it indicates a tendency for electrons to flow from the region with higher Fermi level to the region with lower Fermi level. Using the depletion approximation, we have assumed that everywhere in the neutral region has similar carrier concentration. Therefore, the Fermi level is the same across the neutral region. At the two ends of the depletion region, the Fermi levels no longer align, and the difference between the Fermi levels is determined by the voltage applied to the two ends of the junction. Inside the depletion region, locating the Fermi level is a bit complicated, as there are externally injected carriers so that the equilibrium condition cannot be assumed. The simple Fermi Dirac statistics with one single Fermi level cannot be applied directly. It has to be handled using some advanced concepts of quasi-Fermi levels. To avoid long discussions at this stage, we will again ignore what is going on in the depletion region and just allow the Fermi level to be different at the two ends of the junction. It would not affect the calculations of diode current according to any p-n junction theory described in textbooks. In fact, the depletion region is often ignored in the study of p-n junctions. For example, we have also ignored the number of carriers in the depletion regions when we count majority and minority carriers at thermal equilibrium.